So here you go, a quick explanation of thermal runaway. I'm going to start with the circuit we used in the last lab of Unit 9. So we have a transistor here with DC on the base, steady current flowing. I'm going to heat it up with a soldering iron. And as it heats up, we'll see current starts to increase pretty drastically. And that is base voltage still staying stable. So that is just the heat added by the soldering iron causing that current flow to increase. Now I'll take the iron away, and it starts to cool off. It reduces again. I sped this up so you don't have to watch it take so long. I'll show you again, heating it up, cooling it down, heating it up. Now normally this heat would be caused by extra current flowing. Now here we have a sine wave going through. And as we heat it up, we'll see it start to go close farther and farther into saturation. We see the bottom of the wave distorting, clipping. That's because it's going farther and farther into saturation. Notice also that the wave is getting smaller. We're pushing it to saturation, so there's less room to amplify. We can't increase and decrease current as much as we could before. Now it's cooling off and going back to where it was. So now we're going to listen to what happens with audio going through that circuit.
My heart is saying that it's ready to go. It's too bad, darling, we wound up broken hearted. We're feeling all the same things, we're just out on our own. The rain hasn't started, the clouds are getting darker. I'm thinking that it's time that
So there was a demonstration of thermal runaway, or at least the positive thermal coefficient of a transistor. Normally that heat would be created by current flowing through the transistor. As current flows through the transistor, it heats up. That causes more current to flow, which causes more heat, and that's thermal runaway.